Hello everyone, welcome back to Tales of Chemistry. In this video, we are continuing with non-ideal solutions. Now, the previous episode we have studied what is Raoult's law and what are ideal solutions. Then, what is a non-ideal solution? A solution is said to be non-ideal if it does not follow Raoult's law, if the solution is not obeying Raoult's law. That is, according to Raoult's law, P of solution is equal to mole fraction of solute into pure vapor pressure of solute plus mole fraction of solvent into pure vapor pressure of solvent. This is Raoult's law. So if a solution is not obeying this particular relationship, then we call it a non-ideal solution. For ideal solution, we have studied delta V mixing has to be 0, delta H mixing has to be 0. So for a non-ideal solution, delta V mixing can be greater than or less than 0. Delta H mixing can be greater than or less than 0. That is, it can be either exothermic or endothermic reaction. Now, this non-ideal behavior is of two types. There are two different types of non-ideal behavior. The first one is, solutions that show positive deviation from Raoult's law. First one, solution which shows a positive deviation from Raoult's law. Now, the solution is said to be, showing a positive deviation when at any composition, its vapor pressure, its vapor pressure is higher than that exhibited by Raoult's law. So what does that mean? If the solution is showing a positive deviation, then the vapor pressure of the solution has to be greater than, higher than that exhibited by Raoult's law, which means total pressure of solution is not equal to pressure due to solute plus pressure due to solvent. Instead, total pressure is greater than the pressure due to the solute plus the pressure due to the solvent. Pressure due to solute is mole fraction of solute into pure vapor pressure. Pressure due to solvent is mole fraction of solvent into pure vapor pressure due to the solvent. Now, one or two examples for positive deviation you must study. One example is water plus alcohol, ethanol. Then carbon tetrachloride plus benzene. Third example here is acetone plus ethanol, acetone and ethyl alcohol. These 2 points given here are the conditions for non-ideal behavior. Condition for positive deviation from ideal behavior. Delta V mixing is positive, meaning the volume of the solution is greater than the volume of the solute plus the volume of solvent. Delta H mixing is positive. That again tells us that the net heat content the net heat content of the solution is more than the heat content of the solute plus the solvent. All right. Now, graphically, how do we represent positive deviation from ideal behavior? Now, so the graph, as you already know, is vapor pressure against mole fraction graph. So on one side, the left corner, I have taken x of solute 1. On the right corner, x of solute is 0. As I move from right to left, mole fraction of the solute increases. Therefore, accordingly, pressure due to the solute increases. Left to right, this line represents pressure due to the solvent, and the topmost line that represents the total pressure. Now, what is this corner representing? P naught of solute, pure vapor pressure, because at this corner you have x of solute is 1. So the corresponding pressure will be pressure due to the pure solute. On the other side, the right-hand side corner, this represents P naught of the solvent. So this is explained in the previous video. Now, here, what is the meaning of positive deviation? Pressure, total pressure is more than the, more than what is expected by Raoult's law, isn't it? So here, for the solute, all right, this represents the solute. Look at this. For the solute, the dotted line represents the expected pressure due to or because of ideal behavior. Now, this line which I'm drawing, this curve which I'm drawing, that is the original nature of the graph. As in, this tells us that pressure due to solute is, okay, more than that is expected by ideal behavior. Similarly, pressure due to the solvent is also greater than what is expected by ideal behavior. As a result, the total pressure is also greater than what is represented by ideal behavior. So this is how we graphically represent a solution that shows positive deviation from ideal behavior. All right. Now, there are solutions which show negative deviation from ideal behavior. We have solutions that show negative deviation from Raoult's law, that is from ideal behavior. Now, if the vapor pressure of the solution is less than that is expected by ideal behavior, the total vapor pressure is less than that is expected by ideal behavior, such solutions are called, or such solutions are said to be exhibiting negative deviation from ideal behavior, or a negative deviation from Raoult's law. One such example is a water plus acid, water plus hydrochloric acid, or water plus nitric acid, etc. Yeah, at least one or two examples make it a point to learn. Now, so since we now know that this is negative deviation, and in the case of negative deviation, total pressure of the solution will be less than what is expected by ideal behavior. So that's why it is written here, P of solution is less than pressure due to, partial pressure due to solute plus partial pressure due to solvent. Then, in such cases, conditions for a solution to show non-ideal behavior is delta H mixing has to be negative, delta V mixing has to be negative. Delta V mixing is negative, meaning the volume decreases. When you mix the solute with the solvent, the volume decreases. And accordingly, delta H negative tells heat content of the solution is less than the heat content present in the solute plus solvent. That, in other words, means some amount of heat energy is given to the surroundings. Solution's heat content is dropping. So where is that difference going? That is given out to the surrounding exothermic reactions. Okay. So graphically, how do we represent negative deviation? So now all these points you require no explanation. You know the meaning of the dotted line now. And since it is negative deviation, the curve will be below the dotted line, meaning what you actually get to experience is less than the ideal behavior. The graph here is going below the dotted line. Dotted line represents ideal behavior, but actual behavior of the solute or the solvent here is negatively deviating from what is expected. Yeah, so learn to draw the graphs as well. Last topic for now is azeotropic solutions or azeotropes. Azeotropes are also called constant boiling mixtures. Azeotropes are also called constant boiling mixtures. So the meaning of this word constant boiling is when you boil this mixture at a particular composition, okay, vapors will come out from the solution, but the vapor will have both the components. Generally, when you fractionally, distill something, the one which has, it's separating two liquids based on the boiling point of the liquids, right? So here, but what happens is instead of one liquid, one vapor, okay, vapors of one particular component, instead of that coming out, you will get vapors in which both components are present. So such a solution is called a constant boiling mixture. The solutions of completely miscible liquids which boil at a constant temperature. So when they are boiling, there is no change in temperature, but they distill without any change in their composition. Both the components will be present and there will be no difference in the composition of these two components. Such mixtures are called azeotropes or azeotropic mixture. Generally, this is not asked as a definition. Instead, the definition will be given to you and you are asked to find out an appropriate term for such solutions which boil without any change in their composition. So your answer has to be azeotropes or constant boiling mixtures. Azeotropes are also of two types. One is a minimum boiling azeotrope. As per our syllabus, what we need to know is a minimum boiling azeotrope is formed by solutions that show positive deviation from ideal behavior. So you already know example for positive deviation, ethanol water mixture. So ethanol water mixture is something which shows positive deviation from ideal behavior. Okay, and this will form a minimum boiling azeotropic mixture. What is this actually? In minimum words, minimum boiling azeotropic mixture is at one particular composition. Okay, there will be a particular composition where the vapor pressure of that solution, yeah, that mixture. So that particular composition's vapor pressure is higher than those of the components. So the total vapor pressure of the composition is higher than the vapor pressure of the individual components. And because the vapor pressure is higher, this particular composition will have the least boiling point. So that is a minimum boiling azeotropic mixture. Similarly, we have maximum boiling azeotropic mixture also. Maximum boiling azeotropic mixtures are formed by non-ideal solutions that show negative deviation, HCl and water, HNO3 and water. So here also, at a particular composition, the vapor pressure of that composition will be lesser than the vapor pressure due to the individual components. Okay, so lesser than the individual components, and therefore the boiling point will be maximum. The boiling point will be maximum, and such solutions are called maximum boiling azeotropic mixture. Yeah, that's all in this video. Stay tuned for more videos. Thank you.